Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the benefit of the BSc Physical Sciences students for the paper on applied electronics. In the previous lectures, we saw the Schrodinger equation being applied to various problems in quantum mechanics, such as the particle in a box, and then the hydrogen atom problem, and lastly, now in the present lecture we will be talking about what is called the rigid rotator. So, the contents of the present lecture are the problem of rigid rotator, objective, examples, solution to the problem, eigenvalues, and rotational band spectroscopy. Now, let us first ask what is meant by a rigid rotator. Where do you come across this problem in realistic terms? A rigid rotator may be like hydrogen molecule. You got 2 hydrogen atoms. The example of homo molecule, whereas you can have hetero molecule like HCl or carbon monoxide, wherein one of the atoms is carbon, the other is oxygen, and in general we can have 2 atoms coupled to each other. There is a rigid rotator where you find 2 atoms M1 and M2, the masses are M1 and M2 separated a bond length. This is a diatomic molecule. You see a diatomic molecule like carbon monoxide, or you can have HCl or even oxygen molecule or nitrogen molecule, wherein you got the 2 atoms are identical, whereas carbon monoxide 2 atoms which are not identical, they are separated by a bond length or a distance, or that is a very important parameter, bond length, right, is a very important parameter. And the center C refers to the center of gravity of the system. So, a rigid rotator consists of 2 masses M1 and M2 separated by a distance, or since the distance between the 2 masses is fixed, it is referred to as a rigid rotator. The point I will once again I will go through it. Since the distance between the 2 masses is fixed, it is referred to as a rigid rotator. But in reality, nothing is rigid. Even in the case of carbon monoxide or nitrogen molecule, there will be vibration. You would have studied or will be knowing that in all solids, even at absolute 0, the atoms are continuously vibrating. Therefore, there will be vibration, and along with vibration there will be rotation. Now, we are, for the sake of convenience, we forget or remove, for the sake of simplicity we are removing the M1, M2 are not vibrating. they are assumed not vibrating. So, the distance is constant, it is rigid. In reality, it is not rigid. Okay. Why should we study this problem? Now, if you look at this room, you have got light here. This light that you have got here, the so called spectroscopy, right here have the title as electronic vibration and the rotational band spectroscopy. The light that is incident falling on me, on my face, is due to what? It is due to the electrons which are coming down, right, going up and they may be coming down. Photons are emitted, and in the case of these mercury vapor lamps, the electrons are constantly going up and coming down, and in the process when the electrons are coming from higher energy levels to lower energy levels like this, you get electronic spectroscopy. What is electronic spectroscopy? Whenever you are having transitions coming from the higher energy levels, they are the higher energy levels, to the lower energy levels, they give rise to what is called the electronic spectroscopy. So, the electronic spectroscopy depends upon the energy levels, and in general the spectroscopy that you have here is in the visible region, right, the visible region. I can see all the white light consists of different colors, the VIBGYOR, all these things, you know, this is so called electronic spectroscopy. On the other hand, in the case of solids, the atoms are vibrating, that gives rise to what are called vibrational energy levels, right, or harmonic oscillator eigenvalues as they are called. They give rise to what are called vibration energy levels, and when the atoms are coming from higher energy levels to lower energy levels, you get what is called vibrational spectroscopy. There will be emission of photon, that these photons are due to vibrational spectroscopy, they give rise to vibrational spectrum. And now we are concerned about the rotational energy levels, right. This is the importance as far as our lecture is concerned. You have the rotational energy levels. How do you get these levels? So, the purpose of this lecture is to determine these energy levels, which we call as the rotational energy levels of molecules. You know, the molecules are rotating, right. I showed you about these molecules, that you got two atoms giving rise to a molecule, and this whole thing will be rotating. You can consider this like a stick, and this is the axis. About this axis it will be rotating, it is a rigid rotator, it will be rotating, right. These two atoms M1 M2 will be rotating, okay. That is the so called rigid rotator, right. Okay. The rotation will not take all possible velocities, it will take only discrete velocities, and that is the reason why the energies of these rotators will be discrete. They are the discrete energy levels which I show here. The rotation energy levels will be discrete. We are in the quantum regime. So, when we are talking about the electronic energy levels or the vibrational spectroscopy which give rise to, which is due to vibration energy levels, or rotational spectroscopy which is due to the rotation energy levels, all these energy levels should be quantized. They can take only discrete energy values. You see the discrete levels, right. The discrete energy levels, the electronic energy levels, then the vibration energy levels, the rotation energy levels. As I told you, we are now concerned about the rotation energy levels. Okay. The two masses are found at distances r1 and r2 from the center of the mass. The velocity of the two masses are assumed to be v1 and v2. Now, they are all simple mathematics. The angular velocity v1 will be equal to r1 into omega, v2 will be r2 into omega. The examples I told you may be oxygen molecule or carbon monoxide. The aim is to obtain their rotational energy states or the rotational energy values. Why should you know the rotational energy values? Then only you can find the rotational band spectroscopy. I would like to clarify, the rotational band spectroscopy that you have here will be in the microwave regime. The band spectroscopy, the spectrum that is produced because of the transitions between the various rotation energy levels will give rise to, will be in the microwave region, whereas the electronic energy levels that I have here, the light, that is coming from the mercury vapor atoms, the electrons in the atoms, they give rise to the so called the electronic spectroscopy, that is in the visible region. Here this will be in the microwave region, that is one important thing that should be kept in mind, that is the so called the rotational band spectroscopy. The kinetic energy of the rigid rotator is half m1 v1 square plus half m2 v2 square. So, the total kinetic energy will be half into m1 r1 square plus m2 r2 square multiplied by omega square, or k will be equal to half into I is the moment of inertia multiplied by omega square. Okay. The moment of inertia is given by I is equal to m1 r1 square plus m2 r2 square, and that is I again will be equal to mu times r square, where mu is called the reduced mass of the system, that is defined as the product of the two masses m1 and m2 divided by the sum of the two masses, namely m1 and m2. Okay. I is the moment of inertia, right. The kinetic energy becomes k equal to L square by 2 into I, since L is equal to I omega. There is no potential energy term, because in the absence of external force, the energy does not depend on orientation in space. Therefore, there will be no potential energy term involved here. Thus, the Hamiltonian operator of a rigid rotator is therefore just the kinetic energy operator. You write the Hamiltonian as T plus V, here there is no V. So, you will be having only T, and T, the kinetic energy operator is h bar square by 2m into del square, where del square is the Laplacian operator. Instead of m, you have got mu, mu is the reduced mass. Supposing you are talking about electrons, you will be having m is the mass of the electron be here. Now, you are talking about two coupled atoms, a rigid rotator, a diatomic molecule. Therefore, you have your mu here, del square is the Laplacian operator, and in spherical coordinates your del square, as all of you know, will be given in terms of r, theta and phi. To solve the problem of quantum mechanics, any problem that you come across in quantum mechanics, you usually express del square in terms of spherical coordinates rather than rectangular coordinates. Therefore, you have del square as 1 by r square dou by dou r of r square multiplied by dou r plus 1 by r square sin theta into dou theta of sin theta multiplied by dou theta plus 1 by r square sin square theta dou square by dou phi square. This particular thing you have already seen in the hydrogen atom problem. Now, in the case of rigid rotator, r is a constant. So, do not worry about the first term, get rid of the first term. So, you rewrite del square in terms of only theta and phi, okay? Because rigid rotator r is a constant, so this particular thing will vanish, and so you have del square will be 1 by r square sin theta into dou theta of sin theta dou theta plus 1 by r square sin square theta dou square by dou. There are two terms which you have here, right. And therefore, your Hamiltonian, which is independent of the potential energy term and also independent of the term involving r alone, because r is a constant, leads to this kind of expression that you have here. Since h is the kinetic energy operator, that will be minus h bar square by 2 mu into del square. Your L square, that is the angular momentum operator, will be minus h bar square into 1 by sin theta dou theta, the entire thing that you have here, right. Orientation of a rigid rotator depends only on theta and phi, so that the rigid rotator wave functions depend only on the two variables theta and phi. R is not appearing because r is assumed to be constant. The rigid rotator wave functions are customarily denoted by y of theta phi. Therefore, Hamiltonian h operating on the wave function or y of theta phi will be the energy times or constant E is the energy eigenvalue, E times y of theta phi. So, thus you have the Hamiltonian that you had earlier. Now, the Hamiltonian operating on the wave function y theta phi will be E into y theta phi. If we multiply the above equation by sin square theta, you multiply that and letting beta is equal to 2 I into E by h bar square, the entire thing can be simplified and the partial differential equation becomes sin theta of dou by dou theta into sin theta dy by d theta plus dou square y by dou phi square plus beta into sin square theta into y of is equal to 0. The solutions to the rigid rotator wave functions can be obtained when we solve the above equation. It turns out naturally that beta must obey the following condition. Let us have a short break at this point. Welcome back at the break. The beta that you have got here is equal to j into j plus 1, or in other words beta must obey the condition j into j plus 1. In other problems that we have been dealing with in quantum mechanics, certain things come automatically, the quantization comes automatically through the boundary conditions. Likewise, beta should be equal to j into j plus 1, where j will take only integral values like 0, 1, 2, 3 etc. Okay. So, the values of beta will be j into j plus 1 and j will take values of this kind, and using the definition of beta, your E j, what are E j? E j are the rotational energy eigenvalues. They will become h bar square by 2 I. What is I? I is the moment of inertia multiplied by j into j plus 1. These are the energies of a rigid rotator. They are the energy eigenvalues, right? They are the energy eigenvalues. E j are the energy eigenvalues. They will take discrete values because j is discrete. H bar square is nothing but the unit of angular momentum, that is a constant. Moment of inertia of a system is a constant. The only variable is j, and j, if you remember, will take only integral values. Therefore, E j's will take only integral values, or the energy eigenvalues are quantized. The allowed energies of a rigid rotator are given by the above equation. The selection rule for a rigid rotator says that transitions are allowed only between two adjacent states. They are a very important thing. The selection rule allows only transitions to occur between two adjacent states or energy levels. Where are those energy levels? And we will see diagrammatically the energy levels and the energy level separation between two consecutive states. Thus, when the transition is from a state with quantum number j to one with j plus 1, the energy difference is delta E, that will be E j plus 1 minus E j, the energy difference between two successive eigen values j and E j 1, there are two energy eigenvalues. That will be obviously h bar square by 2 I. You have to have j into j plus 1 into j plus 2 minus j into j plus 1. That becomes h bar square by I into j plus 1. That is equal to h square by 4 pi square I into j plus 1, and j will take values of this kind. E is equal to h nu, and therefore, we can now write the delta E will be equal to h nu. Look at the expression for delta E, h bar square by 4 pi square I into j plus 1, that is now equated to h nu. That is what I am doing now. That becomes this thing into j plus 1. What is nu? Nu is the frequency of radiation which will be coming out when the rigid rotator gets transformed from the eigenvalue being changed from j plus 1th state to the jth state, right. When the molecule is jumping from j plus 1 state to the jth state, during this transition the frequency emitted will be given by an expression of this kind, nu is the frequency. This frequency, as I told you, lies in the microwave region. That is an important consequence that should be remembered as far as the rigid rotator is concerned. I was asking you the question, where are the discrete states or the adjacent states? Now, the adjacent states are found here. J equal to 0, you have the energy state here, at the top J is here, 0 is here, 1 is here, the delta E will be 2B, again this delta E again will be, you know, it is you have the energy difference will be 2B, again here is 4B, 6B, 8B. So, the important point is the energy separation between two states will be 2B, and there are the transitions which are occurring, right. The transitions can be between two successive energy states, and transitions which are occurring between two successive energy states will give rise to a frequency which is governed by equation of this kind, and this frequency will be in the microwave regime. So, that is a very important message with regard to a rigid rotator. So, as I told you at the beginning, you talk of electronic spectroscopy, vibrational spectroscopy, and rotational band spectroscopy. The rigid rotator is a problem which refers to rotational band spectroscopy. The vibrational band spectroscopy is due to the fact the atoms in solids are constantly vibrating. They give rise to the so called harmonic oscillator problem. The atoms are vibrating, they give rise to what is called the vibrational energy levels. You have the vibrational energy levels. Now, here this gives the rotational energy levels. As far as electrons and atoms are concerned, the electronic energy levels, the higher energy levels and the lower energy levels, and that lies in the visible region, but these things lie in different regions. As far as the rigid rotator problem is concerned or rotational band spectroscopy is concerned, it lies in the microwave regime. In general, in many problems you will be having electronic, vibrational and rotational, and mostly when you talk of Raman spectroscopy and all, the vibration rotation will come together. You talk of vibrational spectroscopy and rotational band spectroscopy. What is wave function? The wave function is a thing that cannot be observed or measured, but what can be observed is psi star psi. What do you mean by psi star psi? Psi star psi gives the probability of finding electron at a given point, or a probability of finding electron or a proton or a neutron at a given point, right. Now, we started with the problem of a particle in a box. Particle in a box means an electron bound to an atom or electron bound to a metal. We considered a box of length A in the one of the early lectures. So, x equal to 0 to x equal to A, you got a box of length A, right, x equal to 0 here, x is A here, right. Now, you are asked to plot the wave function. The first eigen state psi 1 is the first eigen function, psi 2 is the second eigen function, right. You are the different energy levels, right, E 1, E 2, E 3, the corresponding eigen functions I showed you in the earlier lectures. Now, we should know what is meant by normalization, the concept of normalization. If the following condition is satisfied, then the wave function is said to be normalized. What is your phi x square dx? That gives the probability of finding the particle in a given region dx. Dx is a distance, or d tau dv is a volume, right. In a given volume, phi x square dx, that gives the probability of finding a particle here the probability of finding the particle between x and dx is obviously phi x square into dx, right. And the wave function that you have got here, you take the square wave function, multiply this by dx, then you integrate this between 0 to a. That means, you are talking about a square well or a rectangular well or a box, right. In a box of length e, you got the particle. So, the probability of finding the particle, the integrated value should be equal to 1. If the integrated value is 1, then the wave function is said to be normalized. Let me repeat once again, you take the wave function psi. If you write psi of x multiplied by psi of x star into d tau, integrate that between limit minus infinity to plus infinity, even that it should be equal to 1. Then if it is equal to 1, it is said to be a normalized wave function. What is that normalized wave function? The psi is said to be normalized. On the other hand, if psi star psi d tau is equal to 2, then you have the integral, same integral, then your psi is not normalized. How do you normalize it? You take this 2 on the right hand side to the left hand side, it will become 1 by 2, 1 by 2 times psi star psi d tau will be equal to 1, right, because you have brought 2 here. What is when by normalized wave function? 1 by root 2 multiplied by psi star into 1 by root 2 multiplied by psi d tau will be equal to 1. So, 1 by root 2 multiplied by psi is the so called normalized wave function. I will now ask you to determine the so called normalization constant. Find the normalized wave function. You can take this as a take home problem. 1 is equal to a square into sin square n pi x by a into dx. It is a particle box problem, right. Here is what the integral in this equation, it is equals a by 2. So, you are asked to find what is the numerical value of a, what is called the normalization constant. Supposing you take a n electron problem, you will write psi star psi d tau will be equal to n, and then what will you do is you take this n to the left hand side, 1 by n into psi star psi d tau will be equal to 1. In order to make it right hand side 1, n should be taken to the left hand side, and 1 by root 10 psi will be the normalized wave function. So, similarly here you have to calculate the solve for A. This is what you will be getting now. You have to have a better understanding of the normalization of the wave functions. We will now pass on to the summary of the present lecture. The summary goes as follows. The Hamiltonian for the problem of a rigid rotator is set up. The energy eigenvalues are determined, rotation band spectroscopy is obtained, the normalization constant for a particle in a box is deduced. The questions are, what is a rigid rotator? Give examples. Is it really rigid? Write down the Hamiltonian for the problem. What are its eigenvalues? What is meant by normalization? With this we come to the end of the section on quantum mechanics. In the lectures to come, we will deal with radioactivity, natural radioactivity, artificial radioactivity, these things more or less related to the nuclear physics, because so far we have been outside the nucleus, we have been talking about electrons which are say outside. Then we have to pass on to the nuclear spectroscopy or nuclear energy levels, about the nucleus, more into the nucleus. These things we will see in the lectures to come. Thank you.